And welcoming Jeff Mulligan. Jeff is the infrastructure management technician for the city of Vernon, BC. At the city, he's responsible for the development, implementation, and maintenance of asset management strategies, processes, and tools. Jeff has a degree in geology from the University of British Columbia and has been working in the field of GIS for over 20 years in emergency response planning, habitat suitability modeling, and within the local government sector. Over the last several years, Jeff has pivoted roles towards the field of asset management, where he combines his passion for geospatial technology and getting data and tools into the hands of the people who need it the most. Jeff, the floor is yours.
Thanks, Marcel. Just share here. So thanks, Marcel, for the introduction, and thanks to FCM on behalf of the City of Vernon for recognizing us with this award and for the opportunity to present our project here today. So just before I start, I want to acknowledge that I'm on the unceded land of the Okanagan Nation Alliance, the Silk. And the Silk people have a great reverence and respect for water, which is what I'll be talking about today. So let's sort of begin with the question to you all. When there's a huge thunderstorm that rolls through your city, do you ever wonder where does all that water go? So I live and work in Vernon, BC. So we're in the North Okanagan, just about a half an hour up the road from Kelowna, population of about 43,000. I've been here for over 3 years now, and you know what has struck me is that everyone here knows how to swim, and that water is a huge part of the Okanagan lifestyle. But when it comes to water, Vernon too has our share of drainage issues, and they're getting worse before they're getting any better. We needed a way to best manage our stormwater assets, so our pipes, our culverts, our ditches and streams. We wanted to better understand where in the city to improve the drainage system, how much will it cost, and when. And that really is the goal of asset management, is to provide sustainable service delivery. And it's tough. Like many cities in Canada, Vernon we have limited resources, aging infrastructure. So we're constantly balancing this desired level of service with what we can realistically afford. We're using risk management to achieve this balance. So in terms of risk, we typically look at, where are the pipes, what material and age are they, what is the consequence if a culvert fails downtown, how much money we'll need in the future, and what will that future look like? So these are some of the questions that we ask. But from a drainage perspective, there's a few other factors that will disturb this precarious balance. And the first is drainage is more complex than just pipes and culverts. So when the pipe system is overwhelmed during a large storm, the major system takes over. And this is what's called Overland Flow, where pipes fill up, streets fill up, curbs over top, and water goes downhill. So through ditches, backyards, into people's basements. It can be very damaging. And when it comes to overland flow and overland flooding, you might not even know you have a problem until you have a problem. The second threat to sustainable service delivery is, of course, climate change. And certainly local governments are on the front lines of responding to climate change. It amplifies risk, and it increases costs required to manage these risks. And drainage systems, quite often, they bear the brunt of climate change. So drainage is complex. This is the hydrology of Vernon. So Vernon is fairly hilly and arid. We're surrounded by 3 main water bodies. We have a very large catchment area starting up near our ski hill, which is called Silver Star, and that flows right down through the city. Kalmalka Lake to the south has lake levels regulated by the province, which control the flow volumes of Vernon Creek that flows into Okanagan Lake. So there's a few jurisdictions involved, few moving parts. So we know where the creeks are, but where are these overland flow routes, the ones that only appear when it really storms and cause significant damage? So earlier studies, like the one you see here, used air photo interpretation to define these overland flow routes. And that's pretty easy when there's topography, right? But can you notice anything strange about this figure here? All the overland flow routes, they abruptly stop when they reach the low-lying urban areas. So we know they reach the creek. So this comes back to my initial question, where does all that water go? Especially in these low-lying areas where most of us live and work, and how do we figure that out? So last year there was a great story in the news about how archaeologists in Guatemala were unearthing thousands of ancient mine ruins that had never been seen before. They literally found like 60,000 new structures. These mine structures were hidden beneath a dense, overgrown jungle canopy, and they were perfectly preserved. In many cases, archaeologists had walked right over them before without even knowing they were there, like this pyramid. So they discovered these vast ruins using LiDAR technology. LiDAR turned this jungle into this. It's like pulling back the curtain. So archaeologists, they used to believe mines lived in these disconnected city-states, but discovery of linear causeways, terraces, and roads threw that belief right out the window. The mine population was by far larger and more complex than they previously thought. So how LiDAR works is that you fly a plane or a drone over an area and you bathe it in light beams. And this allows you to collect elevation information of the objects on the surface. More importantly, it allows you to create a bare earth elevation surface stripped of all vegetation. So somewhat similar to the archaeological project in Guatemala, in 2018, the federal, provincial governments, they funded LiDAR to be flown for the entire Okanagan Lake watershed. So that's from the border, the US border, all the way up to Armstrong. It's about 8,000 square kilometers, huge area. And this was to assist in the creation of flood maps on the heels of a devastating flooding year in 2017. So piggybacking off this project, the city of Vernon, we coordinated extra flight paths over Vernon. And this allowed us to get an incredibly high density LiDAR data set with almost 30 elevation points per square meter. And what that actually allows you to do is to delineate curves. It's that sort of level of detail. So from that bare earth elevation surface, the smart folks at Urban Systems who helped us with this, they use modeling software to calculate the most likely path a drop of water will take from when it hits the ground to when it reaches the creeks and lakes. So in defining these overland flow routes, we modeled a large 1 in 100-year storm event, so a really big one, assuming that the pipe system is at full capacity. So flow rates were calculated based on the size of the catchment area and the peak unit runoff rates, which were a function of vegetation, slope, imperviousness. And the end result, as you can see, is a very detailed drainage network with calculated flow rates. So coming back to this early slide, now we have drainage paths that come all the way down to the creeks and into the lakes. And if we zoom in even further, the level of detail is quite amazing. You can actually see where water pools and where it jumps across roads. So once we know where these overland flow routes are located, and we know their flow rates or how large they might be in a large storm event, we can use GIS and mapping information to assess consequence. So which of these overland flow routes poses the most significant risk to the community? We've made these overland flow routes and catchment areas available through online maps to our planning and development departments, to our drainage and utility operations, our people out in the field. And these are the folks who need the information to make decisions. Coincidentally, on the heels of presenting this report to council, the city experienced 2 significant storm events this spring. During the spring freshet, when the creeks were absolutely full. So we were able to go out and actually ground truth a lot of these interpreted flow routes. They're quite accurate. We've also started recording where problem areas are occurring based on service center call-ins and capturing these on a map. And this is really valuable because these flooding events can happen so quickly, and if they're not documented and recorded, they can fade quickly from the collective memory. So our capital program, we're starting to chip away at making drainage improvements in these problem areas. We're also using this information to avoid drainage issues in the future. So future developments within catchment areas, they need to take into account existing overland flow routes and their effect on what happens downstream, like these bottlenecks. So these overland flow routes, they might not look like much until a big storm occurs. So they need to be designated and protected so we're not adding to the problem for future generations. And we can do that through zoning, through OCP designations, and establishing statutory right-of-ways. Because we're starting to see these large storm events occur more frequently, such as this spring, and that wasn't even a really large event, it's important to apply a climate change lens to the overall drainage system. And this really circles back to the second threat to sustainable service delivery. Climate change, it needs to be integrated into our understanding of drainage systems and certainly back into our prioritization approach. During the course of the study, the city also commissioned a climate change vulnerability assessment. So we explored how is climate expected to change? And multiple climate projection studies are all coming to the same conclusion, that Vernon is expected to have hotter, drier summers, increased precipitation in spring, fall, and winter, and increased frequency and magnitude of these large storm events. So how does that affect the watershed and the drainage system? Well, it does on a bunch of different levels. So we'll expect more fires, and this will result in increased runoff, erosion, and sediment transport following a wildfire event. And this can plug culverts and cause flooding. We expect increases in rainfall event magnitude and frequency, as I said before, and this makes our creeks and our creek infrastructure particularly vulnerable, as well as our natural drainage courses and overland flow routes. So climate change, it is introducing new hazards to the drainage system, and it is amplifying the risks. So by integrating climate vulnerability back into our overall prioritization framework, the city now has a risk-based approach for making improvements to the drainage system. So some of our next steps, we're currently using this new LiDAR data to complete flood mapping studies of our creeks. And you really do need that high density LiDAR data to do that. We're currently in the design phase of a sediment control structure to help prevent the filling of our vulnerable culverts with sediment during these events. And council has supported the recent staffing of a dedicated water resource engineer to make these needed improvements a reality. So these are critical first steps for our future success through a strong foundation of knowledge, tools for decision makers, and making climate resiliency a larger part of our planning process. We're now vastly better equipped to answer the question, where does all that water go now and into the future? I'm Jeff Mulligan from the City of Vernon. Thanks.
All right, wonderful. Thank you very much, Jeff. Very, very inspiring, powerful example of adaptation to climate change, its impacts, and how to preserve our lifestyle. Now, if you have any burning question for Jeff, please feel free to ask, but we're now reaching that time to get into breakout rooms for the remaining time of this session. So I'm not seeing any specific question right now. There we go. Thank you, Sue. 30 points per square meter. How much dollars? How much did that cost?
Well, interesting. It comes back to collaboration, and hot on the heels of that flooding in 2017, a lot of communities in the Okanagan all kind of came together, and they were looking for grant money to do flood mapping. And what happened is it all got coordinated, and the government ended up paying or funding this huge LiDAR project for like $1.5 million. So by collaborating, I think that's how we got it. We basically, the communities got this data for free. at about 12 points per meter, and we just supplemented that within the city by getting them to do some extra flight paths, which bumped up the density, and it was pretty insignificant compared to the cost of the project.
All right, thank you, Jeff. Hope it answers your question. So, seems like it did. All right. So,